Okay, now, I said okay again. We're doing 3 problems, and they're pretty advanced. We will be able to write a solution out, but it involves solving partial differential equations instead of ordinary differential equations, so I'm going to count that as advanced. And then the last one will be, I believe, just an ODE solution. Yes. And the last one will also be a handwritten thing where it's enormously complex. So this will be our first problem, but right, so today we're doing 3 problems. Right, so we're going to do first the elliptic cross-section pipe, which is this flow right here. So that's going to be the elliptic cross-section pipe. Right, and understand that a circle is a special case of this pipe. So I'm all about general solutions in this class, and you'll see that if I solve this one, when I set A and B equal, I get the circular pipe for free. So that's also the power of analysis. Right? Your math analysis fluid flow should be as general as possible, because we're always trying to solve the largest number of infinities of problems, whatever that means. Right? So this is a neat one just because you can see how the generality gives you the most bang for your buck. Then second one, we'll have a rectangular pipe. And that's its own problem because I want to show you how the methods that we'll use to solve 1 don't transfer to the methods we have to use for problem 2, where we have a rectangular domain. And again, in keeping with generality, right, the rectangular pipe includes the square pipe case. Because if you have 2 ratios of like a width and a height, if they're equal, you get a square. So again, I want you to see the power of posing your problems as general as they can be, because if you get a solution from that, that will be all the better. Let me check my mic levels. These look pretty good. OK. And then the last one we're going to do is a very advanced one, and that will be pressure oscillations in a pipe. This is a very interesting problem because, right, by the time we get here, really we've beaten to a dead horse this classic problem of 2D slot flow and even a bounded slot flow with a single pressure gradient across it. The advanced part about 1 and 2 is the fact that your steady state solution is a partial differential equation, not an ordinary differential equation like we had in the last lectures. And then for this one, you'll still have this pressure gradient across your pipe, but there'll be a time-varying component of that pressure. And what we will model and we'll ask is what's the steady state sort of ebb and flow of the pressure waves in the flow. So we won't talk about the reactionary time of like a pressure pulse. That's like an instantaneous reaction of the fluid. But instead, we'll look for that steady oscillation. All right? And just so and I want to motivate each one of these things. So I've chosen this elliptical cross-section pipe because I want it to sort of introduce you to solving PDEs. So I wanted to show that because maybe if you haven't seen it before, it's not required in the class. It's not required for this class to take our PDE course offered from the math department. I highly recommend it. So I wanted to do this maybe just to show you the trickery that happens in trying to solve PDEs. Taking from this example, we'll apply the same methods, right? And then for this one, I want to show you how educated guess helps for PDEs. So this is, again, a PDE steady state solution. It's just how the domain changes. And then for the pressure oscillation, it's, again, the same type of problem that we'll do. It's quite advanced. And it's really involved in the solution itself is pretty gigantic. But I really wanted to take a time. I really like this solution because it's my moment to soapbox to you about making math pretty. I think it's a fantastic example of how you could just run this thing through Mathematica with the boundary, with the domain that you're in and get the answer, right? You can't get much further with your human brain if you don't make some attempt to redefine terms and make your solution look simpler. And then also by doing this, in the end, we'll see that these are really all related. And I can prove to you, and you really see if you ever get a situation like this where you have a constant pressure gradient in some either slot flow or a bounded domain problem, that there's really an overarching form of the solution, regardless of how nasty it will look, regardless of how large that analytical expression would look. And then I'll show you it's really, right, for all of these problems, even this pressure oscillation one, you really just have to look up two numbers. And you can hopefully believe that for the rest of your career. And you won't pay someone to do a bunch of CFD maybe on these for a first principle estimate of what's going to happen. So really what I enjoy about these types of analytical things is, right, I can just show, I can really prove to you that, that no matter what domain that you give me, I can bound this and bound that. So, right, depending on how well you can measure something, it might not even be worth it. But I still see people numerically solve and do like CFD things for this type of problem, which I'm just a little amazed by. Okay, I'm really excited about this one. So again, I'm going to cut these videos up where I'm going to do one problem for like a video segment. So hopefully that works a little better, and then I don't have to keep redrawing things. Again, that was Josh's recommendation, so I'm going to try that. Josh is in the class right now. Okay, so let's begin problem one. Let's do it. We're in advanced flows. Welcome to advanced flows. All right, so here's my flow schematic. I drew a really nice one before I started the video, and it's very important to really, I think, draw out your flow schematic so well, because then the problem's solved before you. This even really does the simplification of the Navier-Stokes equations for me. Okay, I will have some constant pressure gradient across my now bounded pipe. Right? It looks very similar to our 2D pipe now, but realize now that in terms of my boundary, I don't have an infinitely extending two parallel plates. Now I have an elliptical boundary right here. So it's a closed pipe, or an internal flow, which you might have heard before. But for our cases, in the advanced sense, what it means is now my boundary is a closed set. It's an important distinction, right? So you have fluid coming in here. I just did this tank example, but it really doesn't matter for these types of problems, because all you really care about is that you've gotten past this entrance length. What did that entrance length mean? Well, I got to stand that on the side. The entrance length we recall we showed from scaling was related to that Reynolds number, right? So we could show that from just this epsilon term in the non-dimensional equations if I was laminar or if I was turbulent. Remember, if I was turbulent, I had to really put a 1 over p value on here to measure that very tiny number compared to the length scale in the pipe dimension. But for these cases, we'll go laminar. I still think laminar is a pretty good approximation for even your turbulent flows if you're just trying to see what it might be like. So please listen if you even are a turbulence person. I'll put that up. Right. So what was it? Turbulent. Remember, sort of via experiment, you could show that it had the same relation, right? But there was a 1 over 6. But there was a 1 over 6 power on there. Again, remember, this kind of makes sense because at Reynolds numbers, you have, right, for the Reynolds number, turbulent means a very large Reynolds number. So, right, this does kind of make sense where even if my Reynolds number is really large, this becomes like an order 1 value, so I can measure the dependency between this entrance length and this hydrodynamic diameter. Okay, so those are those two things. This is a good check to see if this problem is satisfied. If it is, this would be your entrance effects. And in your entrance effects, what you determine is that there's no changing velocity profile in your z direction. So again, here's my flow axis. I'm going to flow in the z direction. And my cross-sectional I've made in the xy. I've already said I really enjoy Cartesian coordinates, and I really basically do everything in Cartesian. Even though I'm telling you that sometimes things make it simpler, I've just given up, and I'll take it on the chin to do everything in Cartesian. Okay, so I'm flowing in the z direction. What this panel is I'm looking down the pipe, obviously, maybe if you don't see that, but this is now the elliptical inside, so there's fluid coming out of this board at you right now. For an elliptical pipe, the boundary is defined by this equation, and that's another advanced topic of this boundary right now. if you recall, for a slot flow, right, where this extended infinitely out and infinitely in into the board, right, the boundary was really just a line, right, that was defined by an h, right? So when in a 2D case, the boundary is really sort of like a white, right? It's just a singleton set of lines, right? So the set would be like 0 to h. So here is really my boundary, right? It's just 2 points. But in this case, I now have to write, and in this case, the boundary is defined by an equation and a whole set of points, right? Because when I've bounded my set now, right, the actual boundary of the pipe is defined by this closed, right, closed set of points. Good thing I caught that, right? So the boundary is all points x and y in my domain here, such that I equal 1. Hope you remember that for an elliptical equation, right, this is a general form to describe any ellipse if you give me a major and minor axis. Okay, so I'm trying to get across that the boundary on these closed pipes is slightly different, so we should expect a different sort of solution. And that being because now I don't just have 2 points defending the endpoints of my parallel plates. Now it's a whole set of points, right? Any values of x and y that satisfy this equation are the actual boundary of the pipe. I just keep mentioning it's always nice to go in and just really think about the domain of your flow. And you can do it right here, right? Even in my, right, this is just me writing this out, that the domain of fluid that I'm modeling right now is all the points x, y, and z, such that z is a lot larger than the entrance length, or just larger than it. And then maybe it goes to some L, which is a finite value. Now, L could still be finite, right? Because usually for these types of flows, it's all about I don't care where it came from and I don't care where it's going. I'm just looking for that mostly interior of the pipe flow and the velocity field given in there. But I can just make it finite. What else can I describe about my flow schematic right now? I mean, everything's really described, I'd say, here right now. So that's really the problem at hand we're going to solve. OK, so from this problem, we're going to get our simplified Navier-Stokes equations. Okay, and that system is a very similar one. I'll do dimensional because I want to switch back and forth between doing everything dimensionally and everything non-dimensional, because you should see both versions, right? So really from these terms, what you have, because this was 0, the advection terms on the side right died out. The scales involved in the L made that turn out that this is the only important one. For instance, you could write down them all, and you have sort of this, right? We saw it before even in 2D flow. And then for the x1 doesn't really matter, but you have to make an assumption on that. And then we have the continuity. So that's what happens if you reduce all the equations. Where this is my z momentum. Here's the y equation in the set. Here's the x. I have it 0 here because what I'm saying is that there might just be a constant, or it doesn't really, right, it doesn't matter, or it's balanced by just some other term. It's a tricky thing with these bound things. You have to say that there's no pressure gradient across, or flow isn't happening in the u and in the v. And it's actually tricky, I think, to really show that through a scale, why that assumption would hold true. But you can do it. It was a bit tricky. But we should get to just actually solving things. So the main point is that for this type of flow, we don't need to consider the y and the x. And then for these, for the continuity, you get the same conclusion. Review the last lecture. It's the same arguments you do to really conclude that this must be a constant value. Okay, so continuity is only really used to really conclude, really for the conclusions that the pressure gradient, this is really a constant number assigned. Kind of like how we always saw there was a constant pressure gradient going down pipe flow. So this is really the general equation that we have, and by solving that, will give us the flow. if you haven't seen what this means, right? So component-wise, we get this equation. So that's just how, this is just component-wise, this expression here. So it's pretty similar, right? I mean, like for the 2D slot flow, we really just didn't have this. We only had one giving us the ODE to solve. So something has changed now that we have this bounded domain. So I have to describe how all the changes occur on the interior of this domain. I don't just have one. I don't just have one coordinate to care about. I now have to solve for a function of x and of z. So this comes with boundary conditions. The way I'll write that is no slip. Right? No slip's extremely important for outlaw analysis, right? Because it's a physical argument. It comes from experiment, something that we believe in. It's something that sets these equations of Navier-Stokes apart, that I can always assign a boundary condition, and that being no slip. And even if the walls are moving like we saw in the earlier examples, it still really is a no-slip rule. It's just that it's not slipping relative to the wall. So no slip is an amazing boundary condition that we get for free in the equations of Navier-Stokes. That boundary condition comes from experimentation. Okay. And what does this mean, right? So now I'm saying W evaluated on the set of, right, on the boundary set. So again, this is getting across that I'm trying to find this now function of x and y, right? This is my velocity field in the z direction. I'm trying to determine all points of velocity as a function of x and y, so it's a multivariable function. So evaluating now the boundary means, right, if I take any points that are in this set, right, so the x and y have to obey this equation, I have no slip. So that's this notation here where I say, right, W evaluated at this set. Because as we saw, right, the actual boundary of my elliptical pipe is defined by this closed set. This means any x and y such that this is equal. So that's that expression right there. Okay. Gotta stop saying okay. So again, I've blazed through that, right? I mean, but usually when all these situations, you could go from scales to really get this idea that, right, when you have this type of long pipe or long 2D slot flow going in one direction, you can just kind of outright tell yourself, okay, I'm going to be longer than the entrance length. The momentum equation that I care about is the one in the axial direction of the flow. So they're called axial flows for that. So just grab that in Navier-Stokes equations. And then if you're much farther than an entrance length, you're going to calculate entrance lengths by this laminar relationship. Came from a scale thing. I showed you that. And then it just depends if it's a closed boundary, right, or just a 2D slot boundary. The difference being now in this differential operator. And then you assign no slip, and that's your system to solve. So, like I've always said, right, but like I always said, doesn't seem that advanced, but you could just say, haha, I found based on my assumptions, that's a velocity field right now. But this is a chance for me to actually solve these partial differential equations and maybe see how you could do it if you came across something similar. So I'm just going to show you dirty math tricks, I think, so you can see where these things come from. Because it's always nice if you could actually find the solution yourself, and people appreciate that. All right. So let's get to this idea of making this non-dimensional. What should we do for non-dimensionalization? Well, I'll say that the velocity scale is going to be a length squared. So we already saw this before with a length squared. There's some length. Actually, we didn't define this length before. So this is that viscous relationship. This should look very familiar from the 2D slot flow. So, right, nothing crazy there. And then I'll have similar scales like this, where x and y scale by this L value, some length dimension. Now I want to point out that, right, what's a good length dimension I should pick for this right now? It was pretty clear before when you had just a 2D slot flow, right? So in 2D, right, the L was just equal to the height of the distance between the two plates. And that was pretty clear because it was the only height that you had to pick from. But now you have this A and this B, right, or a major and a minor. Right, so you could pick B, you could pick A, or you could pick, right, different ones, right? So you have the situation where the length scale, it could be E, B, right? And I say A or B because this is just one case of an elliptical cross-sectional pipe. So, right, clearly you could imagine I could squish this ellipse, and now A would be bigger than B. So you have to kind of keep, right, you have to keep both options available to you. Second situation is it could be some combination of these length scales to give you one that maybe measures everything, right? That maybe measures everything. So if you were to go through and calculate and do this method we've done, where you try to figure out what your non-dimensional gradient operator is, you get this matrix, you take the trace, you can fit it, right, and that trace of that matrix would be your length scale that would right, work for all of the equations. Okay, well that length scale ends up being this, right? So the multiplication of 2 divided by A plus B, that's a geometric mean type thing. So unit-wise, this still works because I have square length on top, but this is addition, so it's just the length on the bottom, so I still get A length. Okay? You could have other ones you select 2, and sort of this search of length scale is, before we solve it, I think where a lot of the actual analysis is hidden. Because I've said before, people argue about what's the best scale to scale your problem by. Right? So another, right, you could even have, you could choose this, right, square root of it. That's a geometric mean. Right? These are all length scales that you could pick for this type of problem. And it depends on how you solve them. A good exercise is to show that if you do select this length scale, right, that it's equivalent to picking A or B. These ones not so much. So we kind of have that in mind of this length scale. Okay, so I'm going to pick, though, A for this example. And again, whatever I write down on the board for picking the length scale just to be A will be equivalent if I did that A times B divided by A plus B. You could show that if you follow my methods and just pick this. So with that length scale, our non-dimensional equation to solve, again, I find it very important to do these things, and again, see how I'm going like a physical simplification now to the non-dimensional one, right? So now the equation to solve is just this. And then I redefine now this boundary set to be this. So this is a much nicer problem that we have to solve right now. Okay? So notice now what happened here was I've divided it out by all the dimensions now are kept up in this non-dimensional -1, right? And that came from, right, dividing out these scales, et cetera. Right? If x and y are the same length scale, I just have, right, one term and I can make this balance, and that would give you the -1. You can go ahead and do those steps and show yourself that you would have this -1 in here. This really could be a constant, actually, any constant value, and everything would work. Things just aren't as clean. But now let's get into how one solves this. So this is a nice, well-defined problem, right? Everything's star. It's just in pure math world. I even non-dimensionalize my boundary thing. I even have a nice parameter here, A over B. So sort of just bank that. I'll call that a phi now, measuring, right, maybe the size or orientation of this elliptical cross-section. So now you have this partial differential equation. Right, you have a PDE. Right, so we already have our governing PDE, and now we have our boundary condition, and this just defines the points in there. So it's a well-defined problem. We can attempt to solve it. Very important thing about this equation, though, is that it's a linear differential equation. So in terms of solving linear differential equations, one big property that you always can utilize for linear differential equations is that the sum of two solutions is solution of that sum. Right? So if I say that W star is, let's say, equal to a W1 plus a W2, right? This operator is linear, so that means I can solve subproblems. And that's the power of a linear partial differential equation. Is instead of going at this problem, right, which is defined here, I could think of the solution itself being broken up into different parts, and then solve those parts individually. And then, and then if I could figure out what W1 and W2 are solving these PDEs, right? So we like to think of these as simpler problems. So then these, right, these output then the actual functions that are W1 and W2. Well, then I could figure out, right, the full solution because I could just add them up. All this coming from the fact that this is a linear differential equation, so I'm allowed to do this. So that's really the trick that you end up doing here. All right? The trick being that we say, all right, well, since it's linear, I'll break my problem up into two cases. I have a lowercase b. I'll do a capital B, actually, because there's a b right there. So same idea. Maybe I put this negative sign there just because it makes things look a little better. We just sort of inspect linearity right now. I'm not really doing anything impressive right now. I'm just doing every single step so you can see motivation is. This is just a definition of linearity of this partial differential equation, right? And then if I look on the boundary, right? So if I look at this same equation but evaluate it on the boundary, right? Not even on the boundary, right? Just the PDE itself, right? So then this one, right, by a PDE, I know it's equal to -1. Okay, and I have this. And it kind of, right, and then maybe you could see your problem could be a bit simpler if this is equal to 1. So I've just added an arbitrary function. I've split it up. But now I have this freedom, really, to say, well, if this expression is equal to 1, that makes my life a tad easier. Because what that means then is a different problem I can solve. Is this PDE. All I really did is I broke off this -1 term. This is called Poisson's equation. It's a very boring version of Poisson's equation, but Poisson's equation is just this is Laplace's equation, which is, Poisson essentially just add a term on the end and call it his equation. But what I've done is I've introduced a new function b, which is, I'm going to say, a constant equal to 1. And now it allows me just to solve this simpler problem here. So now, right, if we could figure out or just claim or think about a function b such that it's equal to 1, this would be satisfied. And now my new problem would be getting at this w tilde. So now we have to search for this b function. And there's nothing to do but just maybe guess and check at this stage. There are more rigorized ways to do this. There's actually a fundamental solution to this partial differential equation, but I like the discovery part. I mean, you can set anything to be like this, but a general form you see is just this. Well, if it's also, right, if the forcing function isn't elliptical, some elliptical function, then I could get this if I set conditions on this. Right, so now this is just equal to C1 plus. So now I can, right, I have an equation now for these constants if I set this equal to 1. So I'm a bit closer now. How you would figure out that C, right, how you figure out that, like, well, this works, is difficult maybe to inspire someone to do that. But certainly, right, I mean, but I mean, you know, one way you could do it is you could just, like, let's say, integrate this twice and treat this like just d dx, and you get these x squared terms in there. And then you could maybe think of it that way. But having the x and the y be in there is maybe a bit hard to motivate. But certainly you can achieve it if you pick this function itself. There is some other intuition, right, on this that, like, what you really are doing is you're minusing off a constant value on the boundary, which maybe is difficult to understand for now. But again, these lectures are really maybe sort of about actually solving these PDEs, getting the solution, then let's sort of look at the solution to do some things. So maybe I'll stop and I'll just maybe do these steps because they're pretty neat. Okay, so I got one situation and I have what B should be. And now let's do this process where we look at now what everything looks like on the boundary. Okay, so I have no slip. I've just really redefined this. I know this is the no slip I started off with in this problem. Again, I've broken my problem up into two parts. Find the tilde and then this b that I've set. All right, so this is 0, so now I have these things being 0. So I move one to the other side. And I would just have this evaluated on the boundary. We'll just use the b value right here. And maybe I'll write it like this. And I'll write it like this for sort of a specific reason. All I've done is factored out this C1 from the expression. This is just my b, right? And you have to think of these x's being on this set. Right? This was 0, and I've written it like this. All right, well, this is good because right here, we can just look at the two forms of this equation. And then we get closer. Right? Because then sort of right here, our lives are easier if we then just claim this equaling, right? Then it has the same form. So if C2 over C1 is equal to this ratio squared, that would make this whole expression 1, and then I have this just being a constant value if I impose this. Okay? So really, you have two equations and two unknowns now with just these two right here. So where you came from is you broke this up by linearity, and you're saying, I want to get rid of this constant value. You can do that if you have some function that equals 1, and we just found one that works. It happens that it does work because it's the same functional form as the boundary itself, but it just works any other way. And then what you do is now you just do some trickery to actually get another equation for what these functions are, right? What these constants are. And that just comes from looking at evaluating it at the boundary. The arbitrary choice now being that you have to then say, this function looks very similar to my original problem statement, and I know this is always true. So I can make another equation, and everything's simpler if I have this true. So really, you have two equations and two unknowns now. So this one comes out from the fact that we're enforcing that the gradient, right, the Laplacian of b be equal to 1. But I need another one to fix the other equation, right? So the bag of tools, right, the math bag of tools I've always said is 2 equations need 2 unknowns. So we've made another equation by looking at the boundary, evaluating it at the boundary. There was a 0 term. Then I look at the elliptical part, and I just arbitrarily set this. And now the transformed problem is slightly easier. But first, right, we figured out what B was this way. And now we can write out what C1 and C2 are in terms of a phi now. Make sure I have everything right. I switch around a lot. Right, so now in terms of this phi, I have a phi on top. So now I figured out what the C1 and the C2 are of this B function. And now we step back and now we can step back and see what exactly the tilde problem is now. Where now I'm posed to solve this equation. So I figured out some other part, right? In order to solve this partial differential equation, I was like, well, since it's linear, I'll break it up into maybe let's say this, right? The homogeneous, right? I'm breaking up into the homogeneous case and then the extra case. And put a negative in there because things worked out better. You don't have to. You can do it the other way and put a positive. You'd have the same conclusions. So I've broken up into 2 parts, homogeneous part and then the forcing part. The forcing part I had to set by by this quadratic surface. Figured out what C1 and C2 are, and that came from this tricky business where I just said that C2 over C1 was this value. And that gave me 2 equations to have C1 and C2 now. And now I see that this homogeneous problem is exactly this. Now this problem, right, is much, much easier to solve, and any computer would give you the exact same solution. Now I want to maybe just show you why that would be the case, right? Because what this equation says is find me a function w that's find me the function w that has 0 curvature, and then on the boundary is equal to 1 value. So if it's, say, this elliptical situation right here, what we're getting at is that this is an x and a y. That along the boundary on this function, if this is w, it's all just equal to C1. But I also know that there can't be any curvature on this surface on the interior of the domain, right? So really you can conclude this from something called the maximum-minimum principle of this Laplacian equation, essentially saying that the solution must attain its maximum and its minimum on the boundary. Well, if it attains its maximum and its minimum on the boundary and they're a constant function, then that means the function itself just must be then the function itself must be constant. Certainly, right? Certainly, you know, the thing is, the solution we're going to say is just this, right? It truly is just a flat surface. That being motivated by you've made a simpler homogeneous problem along the boundary, it's a constant value. And then you can say, well, if there's no change on the interior of the domain, telling me by this equation right here, well, this also works. Certainly it does work because I could do this operation and get 0, so that's pretty easy. The fact that it's the only solution is something that we don't really care about. I'm certainly okay if someone just recognizes, hey, that would work. I could just make this a constant value. It certainly satisfied the boundary condition. There's key proofs, though, that go into that people were worried about on the fact that if I could just always do that. So maybe that was too quick that was too quick. But if you see the Laplace equation enough, or if you studied it, this system, right, this PDE is extremely simple, only because looking at this one, you don't really know the solution because of this one term right here and this 0 boundary condition. But this one's easy because you can just conclude immediately this. It's just a constant value. One way to think of this is that you've broken the solution up whatever it may be. This is actually W, right? So let's say it's W star. You've broken it up into some constant part, where this is the C1 value, and then this other B part, which has this sort of looks like that. Right? So this is the B thing that we said. This was the tilde. And by linearity, you're saying the sum of these two things gives me the actual solution. Sorry. Maybe that was all too quick. But in reality, I was just going slow. In reality, I'm just sort of going slow to show you how you can really just do some minor assumptions and tricks to solve PDEs sometimes. Importantly, though, we get this nice general solution that is true for any value now. Okay, of this phi parameter. See how the phi is telling me sort of this, all types of different ellipses I could have that are interior of the boundary. Concluding, and the conclusion really being that this is true for all of them. When a is equal to when a is equal to b, this is 1, and we actually get the circular solution. You have to use the fact that x squared plus y squared is equal to just an a, but you can do it. And notice too, what happens is whenever these 2 points are in this set, you get 1 and you get no slip. So again, you see a difficult thing here with this with this partial differential equations, where now this idea of being at the boundary is you have to consider 2 points independently, where if x or y belong in here, well, then I get a 1, and then I have my no slip condition enforced. Good and dandy. All right, and let's wrap this up with just now. Let's look at the solution, right? If we make it now dimensional, at least the velocity, you can always keep the inputs non-dimensional because really everything is lumped up into the coefficients outside. Okay. Now we're at a point we can really show or just sort of look at the solution to tell things about this flow in general. This length scale is a measure of the actual size of the pipe. It could be A, it could be B, it could be some average of the two. For this situation, I've made this A, so I could just think, I'll just write this as A squared, right? What else can we see from this velocity profile itself? Well, you certainly can Desmos this or graph it in MATLAB, and you'll see it's just these elliptical surfaces, right, that are dependent, right, that are scaled up by this first term, and this term just is telling you relative size of the coordinates, and and this value is fun to play with as well. This is telling you really a measure of how actually two-dimensional this problem is versus a one-dimensional problem, like the slot flow. As you see, as B gets larger and larger and larger, this almost just kind of looks like a slot flow in that situation. Or as A gets larger and larger and larger, it also looks like a slot flow. You also see that the velocity profile scales by the pressure gradient in this expression right here, right? And this is this concept of having, let's say, a pressure-driven flow. The idea is the term right in here is the dP dz, which is the pressure differential across this pipe. So that's this idea of pressure-driven flow because my solution scales by that pressure differential. Right? Viscosity ends up being in the bottom, and that was a choice by actually scaling our velocity, right? So it's kind of weird, right? It's amazing to me actually how everything really does come from scaling, because I could have told you, I could have just told you this before, where now all I've done by doing the actual math is just sort of specified point by point what the velocity actually is. You also see that there's some dependence on the geometry right here, right? This is a measure of actually this boundary, or the shape of the cross-section itself. This 1 divided by 1 over phi has parameters that only involve the boundary itself. So that pops up, and then that pops up. So largest conclusions from these pipe flow problems, at least in steady state, is you give me more of a pressure gradient, I'll have faster velocities. If it's a highly viscous fluid at the same pressure drop, right, then I'll have a slower velocity. And all these things I think you can make pretty intuitive. Just the idea that, well, if it's a really thick viscous fluid, right, for the same pressure gradient of two fluids, right, this one's going to go slower because you have a 1-over relationship. Maybe it wasn't obvious, right, the idea that there's no power relationship here. It's not like 1 over the viscosity squared. It's just 1 over viscosity. So maybe you conclude that as well. And this length scale there's as well. But then at this point, right, I already told you quantities of interest are really what you care about. And those are all derived from the actual solutions. So in this case, calculating a flow rate, or a volumetric flow rate, because we're assuming incompressibility, is neat because you get, right, you have to integrate, right? That's a definition of flow rate that we'll use in the advanced class, is actually integration. That integration for this case will yield this slightly stranger Okay, and now why would I want to integrate this to talk about flow rate? We already can kind of see why quantity of interest is far more interesting, because I don't really care what point by point the velocity is inside of the pipe. Maybe you do, but you probably don't care like what's the velocity right there. When would you use that? So by doing this integration and having a volumetric flow rate, it's something more that you can care about, right? And it's more of a bulk property. That in design, let's say, this is far more important than just going like, I need my velocity at this specific y value to be this many meters per second. No one's going to ever say that, right? So these are better quantities. And you can see by integration, by integration, what you do is you get rid of that coordinate dependence of the x and the y. So you integrate out now this cross section of the domain. Okay, L here is actually my A. In this case. And now instead of having, you have the same results, that now you have flow rate is now driven by a pressure gradient, right? So my pressure gradient really drives up flow rate, but now you have a fourth power of the dimension of the cross section. Okay, so if A and B were equal, this would just be your radius. So you get the radius relationship, and then you still get this sort of coefficient in front, right? So this is, we call a C, right? So usually it's better to maybe to sort of just keep this as general length scale. And then for elliptic case, you'll see that this is just the C value right here. And what is C a function of? I want you to remember this always, that really this coefficient right here, right? It's a flow resistance term. Right? This is only a function of the cross section. It didn't care, right? It doesn't care about, it doesn't care about any fluid properties, any driven pressure, any pressure terms. It's just a function of geometry. So this coefficient, this coefficient is quite important. And for this case, I've calculated all of them. You give me any ratio of A and B for an elliptical cross-section, I can make a table, print these things out, and then what you would do as an engineer is you'd have this length scale, right, of the flow. You could look this up and say I'm driving it with a constant pressure gradient, scale it up by this value, and you could just quickly calculate your flow rate now. No simulations needed at all, just algebra and multiplication of a couple numbers. That's it. All right? So it's neat, right? And then the interpretation is that this term for a circle has a specific value, let's say. What does it end up being? So for a circle, I think it's just pi over 8. Let me check again. Yeah, for a circle, just these values. And then in range I have different of those. So there you go. I've just solved all types of smooth type elliptical cross-section values. And really you come to this conclusion that the C value is only a function of this actual curve that defines the boundary of the pipe. Pretty neat, I think. Really solved all of them. Very, very general. Very general. And people now look, this is what you're calculating analytically when you're doing these pipe flows. You're looking for these resistance terms. They're dependent on this. Being able to actually get this, I could do in this case because it was a simple integration, I could do it. They could get more complicated depending on this, how this is defined. All right. Hope I didn't bore you with that one, but it was still pretty neat, right? All we did was we had that elliptical domain, and we solved all of them, circle being a special case. This whole thing about solving the differential equation, it really seemed this educated guessing is what helped us. We just said, well, if I broke it up into parts, I'd have the solution. How would I do that? If I have this equal to 1, and it's just really math tricks from here on out. But you got a very general solution in the end, and we saw that all the dependencies was in the C term that involved just boundary terms. It had the phi involved, so it was a statement about geometry, not anything about the flow. And then we had the pressure-driven forces that were really driving the flow. So everything scaled up linearly by pressure, inversely proportional to viscosity, and all the information's right there. And then the other benefit is then if you integrate your velocity field, you get a flow rate, which is a bulk property, which is something that you care about. So a second problem, and this is just a much nastier solution that we'll have, but I just expose you to the methods and let's say the math step, reasoning step by step of how you would get the solution. So instead of an elliptic, instead of like this elliptic or smooth type of boundary, I'm saying now I have a rectangular duct. This is important for airflows too, if they're really slow enough. It'd still be turbulent, but a turbulent case just kind of makes edges much more crinkier. Turbulent people will hate me for saying that. But so this so for in this problem, I now have this square domain, and I want to show you. Right, this is a fun thing where, remember I had this A and B right here, we're having some sort of phi. And this boundary, right, what was it defined by? This is the equation that defined this cross-sectional. It defines the boundary by this equation. Any points x and y that satisfy this equation define the boundary of my pipe. So one thing you could actually do is you would notice that if you raise the power to an even value, let's say like this, so sort of the largest distance still being B and A being retained, you just up the power. I mean, this actually would look more like this probably actually look more like a 8 or 6. Has to be even, and you would expect this by just doing Desmos. You would see it looks like it's getting closer to a rectangle, actually. And if you really drove it up, you couldn't even see this. They would start looking more and more like points, actually. So like this is actually like to the 12th. So one guess you could make, let's say, to get this solution is you could say, well, could I take the same methods I did for this problem on this domain and just map those methods such that I can just raise the power in there? And then let's say I had some, right? So then in general, you could think of your boundary being defined like this. Right? And then your solution, right? The solution then the solution would be some sort of function of everything that you have, but also an n would, let's say, pop up in there. And then you could look at the solution, and then maybe to get this one, you could try to limit n to infinity. And then you would recover, right? As n grows larger and larger and larger, these smooth parts start performing these discontinuities on the edges, only in the infinite case. Whereas in engineering, you could probably just approximate it. Well, you understand that, right? If this worked for 2, you could try to extend those methods to, like, let's say, try the case of 4, or just try to solve it for this 2n value right there. And you will notice it's not that simple. You can't extend this method. So this method's really sort of restricted to just this elliptical cross-section. Now it's not too bad, right? Because that involves a lot of pipes, right? But really, to get at this square or rectangular domain, you have to do a different method. And I encourage everyone to actually try to do this. I did it, and I was like, oh, I see why it won't work. Damn it. If you could figure out a way to make that work, though, that'd be pretty cool. I'd like to see that. OK? So we need a different method to solve this rectangular one, right? So here's the same flow schematic. We're in the exact same situation, and we will be this entire lecture, actually. But the idea being that now all I've changed is this, right? Really what changed is this, nothing else in my problem statement. I've now just changed the domain of the or the boundary of the problem. And you'll see that it's just different. Right. Now, what do you do? Right. So what you have then is the exact same non-dimensional equation, right? So I'll skip right to that. What do we have? Our exact same thing. Right? And then we need boundary conditions. Now, it's hard to make, it's not as easy to just write this right now. And for this case, we'll have to do something explicit, right? So there's a boundary here, a boundary here, a boundary here, and a boundary here. So there's 4 equations I can assign. Oh, that's the other thing, right? This is really the boundary. So I can go from positive L to negative L, go from AL to negative AL. So really, these 4 walls constitute, right, boundaries on the wall. So assigning no slip here, no slip here, no slip here, and no slip at this wall is still where it would give you this, right, would give you a well-formed problem as well. So maybe I could write that out, but I want to save time, right? But the other thing is what you could also assign are derivative conditions at these symmetry lines. So instead of solving all the values here, all the values here, you actually combine your solution to just this, and then if you solve this, it would just be a rotation around this interior domain. Right? So it's this classic thing. What we're going to end up really solving is just this right? So this is really region 1. So our solution actually is going to look like this. And then what you would do for the full is you would just really rotate it around, right? For a flow rate, right? For a flow rate, you could just multiply by 4, because it'd be 4 regions. So maybe you see this is just really this wedge right here. But the fact that we're going to assign 0, right, or a symmetry condition right here means I could just mirror image this way and mirror image this way, recover the same solution. Those boundary conditions are tricky because they come from, right, because while no slip comes from actual experimental evidence that we have, and it's like this fundamental principle of fluid dynamics, the symmetry condition comes from just intuition on U. The symmetry condition is coming from you saying, I have a symmetrical domain this way and this way, so I can set a symmetrical boundary condition. So what does that look like, right? What that looks like is, well, at x equal to L, for all y, 0. Before I have these 4 boundary conditions. Okay. I have partial differential equations, and I have 2 orders of magnitude, and I have 2 leading order differentiations 2, so I need to assign 2 equations for each differential operator that's of order 2. That's 1, 2, 3, 4. This is just simple no slip. It's just you always can state no slip relative to a wall. But your life is easier in this problem if instead you use this set of equations, and that being that the slope in the y direction at the point 0 is 0. The slope at the point x, What do I have? 0. And then you have no slip just on the other walls. Yes. So this is a, right? Appreciate the, I like this rectangle one because it also gives you an example of this, maybe this symmetry condition you have in CFD programs. What are those really saying? Okay, so for the problem I have at hand with this rectangular domain, I could try to solve, right, all of the regions. These boundary conditions are defining the entire problem here. But I make my life easier where this one only solves, right, quadrant 1. And then I have the physical intuition that quadrant 2, quadrant 3, and quadrant 4 are just mere reflections of the solution that I get. This assumption of having a symmetry condition is based on the fact that at the very, very center you have a maximum shear value, or you have the largest velocity at the maximum. You have the largest velocity in the exact center of the interior of the pipe, because that means there you're the furthest away from the wall where viscous shear forces are large. So the further you get away from them, right, there's less wall shear to be able to reduce your velocity. So there's the least amount, right? You're the first away from the wall where the viscous forces would matter. So right here you'd be traveling the fastest. So there's a optimum point right there. So symmetry conditions also be thought of as that. I think of it that way. So we're going to use these boundary conditions just because we're going to solve it in one, and it makes life easier. All right. So that's good. Scales, right? So making it non-dimensional. I should not use green. Do the non-dimensional problem. We have the same dimensions. Did I write my scales down? Yes. So x scales, let's say, is L, and y I'll have non-dimensionalized by L. You wouldn't pick AL because you always have to non-dimensionalize all your scales by the same number. Pick the biggest one, right? The idea being picking one number. It's better to scale, right? It's better to scale by one length dimension instead of separate length scales. Multiple velocity scales are nice, but you're making your life a living hell if you do even multiple length scales. Still small parameters pop up, but right. So you have the L, and then the W is the same pressure gradient that we non-dimensionalized by before. Right. So then I have the same situation where I'll say that W scales, right. Right. It's the same sort of viscous force that we had before. This pressure gradient really is the number that you show from continuity. The negative ensures that a negative pressure gradient corresponds to a positive velocity. That's why the negative is in there. Length scale squared, mu. So we still have those same scales. All right. So then what you have is the same equations we had before, right? It's exactly the same. You just have more of these boundary conditions that you're assuming. So for this solution, we will again the same concept where we're going to use nonlinearity to make our life simpler for the problem. Right? Now this one is where you could really see how where something would really illuminate itself. Right? Because we have, I'm going to do that the star, I want it to be equal to a homogeneous part sum Okay, this is exactly what we stated before, where you just want to find some f function such that this is true. So, there are a lot of these, there are a lot of these that would work. I could do 1/4. Okay, two derivatives here gives me a 2. Two derivatives here gives me a 2. gives me a 2. So I have negative 2. So I have negative 4 over 4. I get negative 1. That works. Another one you could do is this would work as well. Another one would even be this. Right? All of these satisfy this. And they're all from you selecting what part you want to remove off. So you're looking for the homogeneous equation, and then you're subtracting off this forcing term right here, right, by just enforcing some other part, right? Think of this as almost, I like to think of this as almost like an initial guess of the solution. Because it's a simple enough problem, right, you could have it be the homogeneous part plus like some guess of what the surface you think it would be. And then what this would be doing is it would be correcting your guess exactly such that you have the true solution. So the easiest pick, right, the easiest choice, if you just did all of them, you would see this actually is a pretty nice, this makes it a bit easier. There are more advanced methods to actually solve this, a more general way of solving this where you're not doing this guessing and checking. But in this class, I think I at least want to encourage you to play with math, and that's what these examples show. Playing around in math can get you somewhere. Right? People have formalized on how to actually solve the Laplace's equation and Poisson's equation, but they got there by looking at a bunch of solved examples. All right. So what do I have here? If I do the transform problem right, again, we have this. This is equal to negative 1. So now I have this homogeneous equation to solve with boundary conditions. Yeah. Here, I'm just writing out my boundary conditions for this homogeneous equation I'm trying to solve. Okay? So this being general for any 0, I have my 4 equations, this being 0 as well. So this is my simpler problem I'm going to solve for, right? Again, realize you've bent linearity where I had the negative 1 term in front, but what I've done is I've just said, well, if I could make this function equal to negative 1 after Laplace has operated on it, life's easier. I'm picking this one because I've done all 3 of them, and you kind of see that, like, it makes it a little bit easier. Especially when you calculate these Fourier coefficients, which is later, right? But any of them would work. Any of them will work, and I'll show you where the difference is later. But we're going to do this one, and that's what I have in my notes. Any of them work. Turns out that you really want it to just be one. You really want it to be a function of one variable that it works, and that's what's making the life a lot easier. All right. So now I want to show you. Right now, the idea right here is you're kind of stuck here. We have nothing else to go off of. Right? I mean, this came around because of your assumption that you made. And this is the educated guess part. So what people did for the longest time, always got to make sure I'm recording. I just thought about that. I am recording. What people did is they were like, I have no dong hecking clue on what this solution looks like, but what if it looks like this? The multiplication of 2 functions. Okay, this is the educated guess. All differential equations are done with a guess and check thing, right? Where you just assume the functional form of what the solution may look like, motivated by anything in modern day, right? So this is called separation of variables, where my function was a function of 2 variables, but I'm saying, right, I can get that functionality by multiplying 2 independent functions together, and that's what my solution looks like. Really, you're searching for a solution, and you're saying, I'm searching for a solution of this form. So just, right, the idea is you make this assumption, and then you plug and chug on that. And if you plug and chug on that, meaning you just like take this expression and plug it in, you'll have this relationship. This is just here, over there. That's the relationship you end up getting. So this is just from making this assumption. I plug it into there. No consideration of boundary conditions yet. Always with differential equations. Leave that for finding constant values. What you've done is you've made the assumption of what the solution looks like, and you plugged it in here, and you go like, OK, well, I now get this relationship. Okay, this is the same sort of thing we did with pressure, where to conclude that pressure was a constant value. Over here, you say this is only a function of y. Right? And on this hand side, this is only a function of x. Right? So you need to logically then conclude, well, the only way this is going to be true, regardless of what x and y I put into the function, is if both of these are equal to the same constant value. I can say that over and over again, but you should maybe just appreciate the idea of this is a function of y, this is a function of x. This ratio, the only way this equality could hold is if they're both just equal to some constant value. Right? Let's say a plus or minus a lambda squared. This is really an eigenvalue. And the conclusion that this being a constant value, this is just a number, right? As long as the real number's here, is coming from this subbed in there. Look at these ratios. This side is a function of only y, and right, it doesn't care about, well, this is only a function of y, only a function of x. The only way that could be true if it was just equal to a constant value. A little bit of a tricky argument, but you really, right, but if you stare at it long enough, you can say the only way I can satisfy this for all x and all y in the domain is if they were equal to constants. All right. I actually love the extra credit. Extra credit being show that there's no negative eigenvalue, right? There's no positive eigenvalues. Did I say negative in there? Yeah, positive. It's a great, wonderful, reminds me of the good old days of my math classes. I just love this proof of just showing from this consistency of this form to show that I don't have positive eigenvalues. This is kind of fun. Am I slow? I'm just slow today. All right. Better one. Okay, so this what you end up getting then is if these are constant values, I now get two ODEs. Okay, this is the PDE. I broke it up, and now I just have two ODEs to solve. What are these two ODEs? They're this. Okay. This is a trick you always do where if you don't know the sign of a number, you say the number's squared and then you leave the sign in the plus or minus. You do the same thing with the square root, but just if you're wondering about that square thing, it's a thing mathematicians do where if they didn't first know what the sign was, you call it a squared number and then leave the plus and minus in front, and then you do conclusions based on this number you know being positive. So that's where the proof comes in that you show that there can't be any positive eigenvalues or positive values of this number. So these are the two ODEs that you must solve. And you solve them. You look them up. They're pretty simple. And you would then just have the general form. So then, in general, okay, this is a multiplication. I have room over there. So right, you can find the general solutions of f and g, right, by a sign and this. So the negative and positive change it between a sign and then these exponentials. 256 lets right, our differential equation class gets you there specifically. All right, so right now I only have I just have this value that I have any constant value right there. And I have this now general solution of at least this part right here. But that was for any arbitrary constant lambda that I picked. Right? So, and again, with linearity, I could sum up all of these, right? So, right, this is some solution right here where the lambda is arbitrary, right? But I could sum up all of these if this was star, star, and leave this, let's say, an I. Still a solution, right? I could sum up all of these values that I picked to be lambda, and then my solution would still be true because of the linearity of this differential equation. So finding some sort of way then, it's like, well, I couldn't just pick one eigenvalue. I needed to somehow find all of the eigenvalues. Right? These eigenvalues don't really care about what they don't worry about what they actually mean. The idea is that you have that indeterminacy that happened from the structure of the equation, right? If here is my line of right? This one would be true. I mean, here I still get the relationship. So this is a lambda 1, right? And then still I could then still say this, right? I could still have this be a lambda 2. So like this idea of counting these eigenvalues is non-trivial, right? It's a lot of math goes into showing you can count them up and it will work. You'll recover the true solution. Proving that these eigenvalues exist and that they are separable and that you can count them up is very tricky business. Okay? And remember I had those constants A, B, C, and D. How would you get A, B, C, and D? Well, of course, you apply the boundary conditions. That's how you get integration constants. You say, right, as y is equal to A, this has to be 0, conclude, conclude, conclude. And then you get down to this. Okay, let me get this. Some number. I'm just going to remove these boundary conditions. Okay. And this is just from solving, right? You get these A's and the B's and the C's and the D's. One conclusion that you have that B value equals 0. And that comes from one of the boundary conditions involving the sign. Okay, so then for this form right here, we get one last equation, one boundary condition application. This being at A. So right, if I look at this value right here, any x, but if I'm at the value A, I have no slip. I'm looking at this form of the equation, that zeroes out when you get here. This being non-zero here. So now you have this infinite sum. Still the same stuff, right? Because this is arbitrary. It needs to be true for any x's I plug into this thing. And then you do this sort of very classic math thing where this is not a non-zero number, right? These are all non-zero numbers, or else I would just have, right? So you could have a trivial type of solution where just an is equal to 0, but that wouldn't be true because then this is only solving one part of the equation. So you'd be throwing away this correction term. So that would mean that this has to be 0. Right? So if that needs to be 0, then you can solve for what all of these eigenvalues are. And they're all the values, right, that make this input to cosine equal to be 0. So that is this. Okay, so the eigenvalues come from the fact that when I apply this boundary condition, I need it to have 0. I need to have no slip, right? I have this infinite sum, right, where n being 1 to infinity, right? This summation coming from the fact that I'm just going to suppose that if I add up any of these constant eigenvalues or lambdas that I have, my choice, I would approach the actual solution but this is just coming from constructing things. And then you apply one last boundary condition after you've gotten rid of b. You found out what c and d are, and that pops up from here. And then you have this conclusion that for this to be 0, this is a non-zero number. This is a non-zero number for all of x, or in general. So that means that this has to be 0 at every term in the sequence. And then that's just a simple equation you solve, because you would go, when are all the times cosine is equal to 0? All the times cosine is equal to 0, right, is when this input argument is equal to pi over 2. It's a beautiful type of process to go through that no one does anymore, of finding eigenvalues. Everything came from me assuming what the function looked like, by the way. It's very important. So then I figured out what at least the lambda n's, what each eigenvalue was, and then one of the last things to do is to satisfy the end boundary condition. So that would be when this is equal to 1. So when that happens, you get this setup of I have another no-slip condition, only this one coming from x star equaling 1. So now I look at the boundary condition where I'm all the way of x star being 1. That goes away. This remains, right? Now it's for any y, so this will remain, but I know what the lambda n is. So now I have an an. An, here's the y star specifically, and then, so if this is equal to 0, negative right there, and then I have to pin down what these an's are. I now need to make this equality true. And this equality being true is done with using a Fourier series, and the Fourier series are Fourier coefficients. All right, so the idea of, I could divide out, so one thing I could do, I could divide out this term. This is just a number right now. This was the same number every time. It was lambda n. No, not yet. So I want to call that. I'll just call this, I don't want to write it a bunch. So for each n, I know what lambda n is, It was that 2n minus 1 with the pi term in there to make the argument equal to 0. And now we have to make this equality true. So what you do there is you multiply the whole equation by these cosine functions and integrate over them. Or you go and you look up what a Fourier coefficient is. I'm not sure if I have to teach this class what Fourier coefficients are. It certainly would be nice, but in terms of keeping modern, I think if you're in a stage of analysis and you're wondering how to do this, if you ever see these expressions and you go, oh, that's a Fourier series, what you're saying is, I'm going to approximate this polynomial equation by an infinite series of cosine terms times some scale term, and then times some amount of coefficients I have. So you're trying to then figure out what these an's are. Well, that's a Fourier problem. You would go in some book you have or text, and you would see that the cosine, these an's would be equal to whatever function you have So this would come from me multiplying through a different lambda n, so let's say a lambda m, and then integrating the entire equation, you get this relationship. And when you do that and actually perform the integration, and maybe at this stage I don't actually ask you to do it on a test or something like that, because I'm not testing your ability to integrate, as long as you would know how to program that. Even in Mathematica, you can just plug this into Mathematica and go what them Fourier coefficients? Tell me, and it'll tell you. So you can even get at that point, but maybe just realize that it's coming from that integral expression. Then you would be able to even figure out what these Fourier coefficients are. They are this. Beautiful. So I have this infinite series solutions now, and I've really defined everything. I left this up top because what I want to sort of stress is, right, this is the solution. Okay, with everything being defined now. I have these expressions right here. I know y star. I told you before, I even know what these are. I did that through it's over 2. There's an over 2 there. I always forget this. Yes, there's an over 2. Okay, so this is my solution right here. I had yet to define really what this lambda n and a n are, and they came from boundary conditions, so you had 4 equations to apply. Take that general form, apply them. I can pin down what these are by a 0 condition, and then the a n's come from integral Fourier coefficients. What were they? What were they indeed? And then you just have some definition for them as well. So everything's defined then. I have the solution. I have the actual analytical solution. It's in the form of an infinite series. It's an infinite series because of the idea that it's a linear partial differential equation. So whatever lambda I picked, I could sum up them all, and that would be the actual solution. The idea that I could count these eigenvalues is non-trivial. The idea that these eigenvalues exist is non-trivial. People worked hard on showing this is the unique solution. That's also a neat, wonderful proof. Okay, then it's a matter of just representation, right? What are nice, cleaner ways to represent this solution? And that's an introduction to, let's say, maybe a bit prettier math, I think. It's always nice to do that. This term right here has a hyperbolic interpretation. So you can actually write this like this, with this cosine. Same setup. I have the cosine, and I have a ratio. Okay, hyperbolic cosines are just a hyperbolic cosine is a exponential, a summation of exponential terms. So this identity is something you could just look up to represent this as like this more compact sort of functional term. It's nice to see it that way only because it's a bit easier to integrate. Also, you see the pure dependence on just the y part and the pure dependence on just the x part. Notice here, if you were programming, you'd have 2 functions to actually define where x is. It's not that hard, but like if you just had pen and paper, it's really nice to have all the functionality just in one part and then the other part. And what was this? This was exactly that guess function that we had before, right? Right? That's why it ends up being easier if you do it this way. And you realize another reason it's easier that this is a function of one variable is that these coefficients came from a Fourier, from a Fourier integral. You can do double, but it's a bit trickier. All right, so cut to the chase. I think this is awesome. I haven't been excited enough for you in this lecture on getting these infinite series solutions. I'm just a bit tired, I think, actually. I actually love this stuff. But this is the solution. I've now defined the entire, w velocity with x and y, and I have this infinite series terms, and it looks just kind of compacted nice. But where we get into, the idea is this doesn't matter. What matters is really this volumetric flow rate. And even in this situation, it looks exactly the same. Dimensionally, after you redimensionalize, it still looks like this, where I have this L to the 4th over mu dp over dz, and then some sort of non-dimensional geometrical expression, where this, after integration, you can do it in Mathematica. Extra credit, go ahead and do it. Give me your workbook. Looks like this. Ta-da. Okay, so before, remember that this is coefficient. This is the exact same thing I talked about with the elliptical case, right? Where my c is only a function of my boundary. In that situation, for that problem, it had some look to it. Or was it? Let me get that thing back out, right? Right? For the elliptical case, this thing looked like 1 over square root here, and then a plus 1 this, right? This was for all ellipses. I could get this c by this. For a square, same situation. Right? Same situation now where the c is now a function only of the a. The a is only a function of the actual boundary definition itself. And it looks like this expression right here. So the a pops there, so geometry pops up right there. And then the structure of equation pops up here with these lambda n's. Notice this expression right here only cares about the eigenvalue, not the a. The a popped up here, where it has some sort of look of like it has some sort of look of a sphere, maybe interpretation. We'll never get around to it. And then for a square, this value is, so you've made, 2, 3. Okay, for a square when a is equal to 1, so the ratio of L and A is actually just 1. There is a specific value for here, it's about 523. And just through calculation, you show these things. Big takeaway, though, right? And I kind of want to stop here just on this steady state pressure-driven flow through a pipe, because hopefully you realize now that I give you this through scaling every time, right? This came from just redimensionalizing the velocity. And then everything we did, right, with these infinite series, right, was a method to calculate this frictional, right, this velocity friction coefficient, right? Even the elliptical case and the square case, right? And I have formulas now for this c is this infinite series, and for elliptical case, I have this nice just ratio of terms right here. But whatever these are, actually, you could show and just do a large range of these values, right, where you vary quite heavily on everything. Where there's a right here, right? So, right, you could just do a large range, and I think even what I had was like, in both cases, it's right. I couldn't find ones that are bigger than this, right? This is any shape of the elliptical pipe or square pipe you have. This coefficient really, you see from all solutions, right? That the frictional coefficient is an order 1 term. So I've given you 2 exact identical analytical expressions for the flow rate velocity in a tube, and I've even shown you that this term is all you really care about, this friction coefficient. Why? Because this just comes from scaling, right? This comes a priori to anything determined in the problem. My L, right, my L comes from just no flow at all, just how I drew a boundary. The pressure gradient is something that you assigned as well. It had to be constant, and it's just telling you how fast or slow pressure is driven in there. So it really is all a lot of just getting this C, right? This resistance coefficient, they call it, flow resistance. Now for a rectangle, it's this infinite series. For ellipses, it's this infinite series. Excuse me. And then for all of these cases, even the ellipse and the square, right? Even the ellipse and the square, it ends up having a situation like this. It's never going to be 0, and you can tell, right? It's pretty easy to see why it would ever be 0, because I can't have a geometry unless there's no geometry at all. If this were to be 0, that would mean, let's say, I would zoom this in, and there'd be no flow rate, right? And it can't be, and it's bounded as well, because if the geometry being, of course, it's infinite, right? But it doesn't work that way. This is the important thing, is that these friction coefficients are really these weak functions. They really just function. They're really just an order 1 term that comes in around. So for steady state flow in a bounded domain in pressure slot, or in a pressure slot, or in a bounded domain, or in a 2D flow, right? I really just wanted to get to the fact that if you're at your office, just write this down. Right? There is a C there. There's some friction coefficient right there. And it's usually about 0.5 or something like that. You pick your favorite one. So even to see like what's happening in the flow sometimes, you could just make it 1/2, 1/4. But I just, just through the solutions themselves are screaming that at you, that it's a lot of work to really calculate what the coefficient is. But in reality, the scaling gave you, right, just this term. And the c was just some number like 1/2, 1/3, 1/5. So I would say we've totally solved this problem of, right, pressure-driven flow in a duct or pipe at steady state. I have solved infinitely number of problems, whether it be in a square domain, elliptical domain, 2D domain. I've solved all of them. Now a really neat problem, I think, which is this pressure variation as a function of time. So we'll do a 2D slot flow with the idea, as I showed you with bounded versus 2D regimes, where it essentially was the simple versus the complex in this case, how the methods still extend where you can write something down, but there certainly are more advanced methods to write down the bounded regime because you have a partial differential equations. So I'm going to do the ODE version, which is going to be this one, but it'll end up being a time-varying partial differential equations. So this situation, I have a bunch of examples in the notes, but I've really taken a long time with this lecture, and I don't know why. I think I'm going to go drink some coffee or something after this to just maybe get hyped up enough for you. But I have these examples of this idealized of time-varying pressure gradient in the axial direction. Just pops up a lot in the idealization of some type of flow. Your heart, right, for instance, it's just exactly that if you looked at the artery coming right out of it. Your heart provides some peristaltic, right, sinusoidal pressure differential as a function of time, right? And then that means the shear stresses involved in the veins in your heart, right, are related to that velocity field within the veins. That's a bounded problem, right? In terms of a slot, I had this example of like the bottom of a lake. If there's a temperature variation, you could drive flow by some variation that way. Or just some type of an undercurrent where there could be a sheet of liquid, right, that varies like on a weekly basis where it's really, really slow, let's say. The idea of this frequency of this time varying pressure differential is also important. But all that stuff will actually come out from this solution, okay? So in the idea of jumping right to it, let's just write down our governing system, right? I'll keep my dynamics this time. All I'm left with is my ODE, right? So the only momentum equation left is the U, right? So the only momentum equation that will matter will be the axial one when you have this when you have this setup of a problem. And we see that from the scales, but I'm done doing the scales for you now. So you're only left with this. So you have a continuity. All the continuity equation will do for you in these situations is tells you from the y and the x that this is only a function of x, that u is not a function of x, et cetera. This being a constant number now. It's not a constant number now, but all the time variation is kept up by this term now. Okay, so this is now a constant number that I'm going to call this, and now there's a variation involved in there that's only a function of time. There's no y in here at all. So that's important. So this is the governing equation and symmetry conditions, maybe you saw before. Comes with no slip, and I'll do a symmetry condition this time. Makes the solution look a little more symmetric, which is kind of nice, right? So right now I'm doing the 2D slot flow where I look at the very center of my slot, and I go from h to negative h. Right, so applying these boundary conditions is just a different representation of the solution. So this is a no slip, right? And this is the symmetry. Right? Symmetry I'm only applying because I know for a fact that my domain looks symmetric. It's a 2D slot. So there's a mirror image going on in my solutions methods. So this is our governing system. And we're still going to utilize linearities, right? And we're going to utilize it by just playing around. This is still a linear equation right now. I have no u squareds involved. I have no square of a derivative term. I don't have a u times a derivative term. So a summation of two functions would still satisfy this equation. So what we're going to do is break off then, right, this expression here. So if I expel this out then in this term, right, sort of a constant value, okay, so I've just expressed this thing out, right, time varying part, and then this part. Okay? So we're going to find a solution that looks like, right, a u1 and a u2, but instead of having this constant trickery or something like that, this time I'm going to have u1 solve this problem. Now that problem I've solved for you enough times in 2D, 3D flows, etc. Right? This is just the steady state flow we've solved for the last 3 lectures. So this one is going to solve this problem right here. And then I'm going to have this problem solve this situation. Okay? And that's summation, right? So again, U2 is solving this part, the time varying part, and then the dynamical part. So I already have one of the solutions, that being this one right here, the quadratic velocity profile that happens in the 2D slot flow. I already have that done. I've done it 3 times over and over in the 2D slot flow. So all I'm looking for then is this dynamic part where I can just take that constant value away. So all that to just sort of come down and say that my governing system looks like this. Okay, that's just the governing system. You could put a U2, you could put a U2 or U1 on here, but the idea being that the U1 is something that we've solved a bunch of times before. So this variation is just going to add on top of that the solution that we already have. Maybe I can expel the solution by the time we get to it, but for now, let's just chug ahead, right? So first, non-dimensionalize. Non-dimensional time is this right there, right? A frequency of a time. So that's sort of just given to you right there. Y kind of says, it speaks for itself. Non-dimensionalized by the height of the slot. It could be a 2h, but it's always nice to just put 1 values in your non-dimensionalization, so that will just be an h. What should that be? Okay, this is a new territory for us right now, so we'll go ahead and just solve it via scales. If you don't know a velocity scale, find the internal one here. And now we get options, right? So I have a u0, order 1 derivative term. Okay, I still have this g expression. And then okay, that's what I have right there. Good, 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 good. This is just going to be, see that, divide everything by the g. So this is now g as well. So now I have 2 options for a velocity scale here. Okay, I don't know what u0 is, but what we're trying to do is assign it, right? So you have, right, I could make this the order 1 term, right? So that could be that this is going to scale exactly like that, right? Makes sense because the u here, that cancels out, I just get 1. Another option is I could have this be the velocity scale. We've already seen that quite a bit, so somebody should be able to quickly say that velocity scale, yes, that velocity scale, right? If we scale by this term right here, this is sort of the dominant type of velocity happening in this type of flow where I have variation in pressure. But that's not quite what we're trying to analyze in this problem, right? Because we want to care about variations, right, or time-varying pressure gradients. So frequency should certainly be part of our velocity gradient. If you're just throwing that information away, it doesn't quite help you. So this one right here, that scale of velocity really corresponds to just the last problems that we've been solving, right? If this truly is your scale for velocity, that means that like the frequency is so low that this one didn't really matter at all. It's really this one. So for like geothermal flows where omega goes up, 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 or like yearly timescale flows, it probably is more looking like this. But for very rapid type oscillating flows, if you have a very thin sheet with like a quick peristaltic pulp thing happen through here, this is more of the velocity scale you're looking for. And then I have my own that I did sort of with the pressure one. You could just look at the average of both of them, right? Okay, and you could do something like that as well. This one's nice because I redid everything using this scale, and you can kind of have, and then you can see that you have this order 1 term that exists in both limits, right? Where if the ratio of these velocities goes to 0 or infinity, it will still retain. You get the similar, you get the exact same solutions. But this is one, just from that discussion, that you probably should expect that, right, that we should certainly in our analysis look at that velocity scale. Because this one I already have done that analysis, and all it was really telling me was the fact that, right, it's a pressure-driven, right, it's a viscous pressure slot, viscous pressure system in a 2D slot or 3D slot. This is the velocity scale for that system. But I'm adding time transients in there, so this is probably more so what I'm looking for. At least I want to model that. OK, so we're going to pick that one. Right? And that makes this 1. And what does that make this expression here? Right? So my u is going to scale like this pressure gradient over this. So now here, I'm going to get this g. Right? So I have a g omega. Notice what happened when I scale that way is the g goes away, and I'm left now with just boom. Okay. Now this quantity right here can be thought of in 2 different ways just by looking at the units of it right now. Okay, what is this exactly? Well, unit-wise of this parameter that we found, which is a viscous term, a kinematic viscosity, or dynamic. I think it's a dynamic actually. Clearly, I'm solving a dynamic problem, so it's probably a dynamic velocity. Always forget, look it up in a textbook. OK, so what is this? Well, I have length squared over here on the bottom. And then this ratio, right, what did we say? This, right, kinematic viscosity is a length squared divided by a time. OK, and then this is, right, and then here I've divided by a time. Have I done that right? This is a 1 over time. Yes. So I can think of it as a square of what? Right? If I consider crossing out these time variables right here and think of it just as lengths themselves, what would I have? Right? So this one clearly is just the length of the slot. Right? And then this expression, right? So then this other length I have, right? We saw this before in the oscillating pressure gradient, right? In terms of the scales, this is a viscous diffusion length. Right? That's what this expression is, and that's what I have right here. Okay, so now this ratio I've had right here, I already have an interpretation of what that parameter is. It's a battle between the size of this h, right, the size of this slot length, versus the size of the penetration depth of those viscous effects of the wall. That's what this ends up being. And this length scale is now dependent on the frequency. Remember when we had the oscillating plate, I had this, I asked you, right, how far up does the mixing occur, or does the oscillations occur, and it was dependent on frequency. So you see the same situation here, and it has a squared term in there. OK, so we want to describe this then as a ratio of lengths. It's nice to have it be 1 over, though. Right? So this could be expressed like this, where my capital gamma is what? It seems tricky, but adding this half in there is a process of making your math look good, where I just have one length scale, and then this would be OK, this is what I'm defining now as gamma. Notice when I square this and put the 2, I recover the exact same expression. But now I just have this one term gamma to look at that I'm defining. You could have just expressed this term as gamma as well. But since it was length squared, you might as well, right, just look at the actual lengths occurring right now. Right? This is a squared parameter. So right, I'd rather just look at the actual ratio itself. And it might save you time later when you're doing those comparisons, right, in your analysis. I mean, this parameter right here in any analysis we have, I just have slot length and then a viscous diffusion length. So saves you a little bit of time, even though there's a squared in there. But the reasons people do this is nothing more than they have a preference of their description of the mathematics. And that description is extremely important. Right? Making your math look pretty helps other people appreciate it. Okay, all this is just say I just have, right, I have some interpretation of at least what this parameter is what all you need to stop and do when you do this non-dimensionalization to get this term right here. So that's my governing equation right now. It's a partial differential equation, right, with time and of space, and it comes with boundary conditions. Also would come with initial condition, too. Should we care about the initial condition? Right, initial condition would be the startup, right? So initial condition for this type of problem is the actual beginning of the oscillation. But we're not concerned about that startup problem, right? We already looked at startup problems in this situation. What we're considering is that I just have a steady state oscillation that occurs every week, every minute, every day. Right? So what does the solution look like with that viscous, with that total balance between the viscous forces and the transients of the pressure? Again, what I'm just amounting to is I'm saying I'm not going to write down the initial condition for this problem because I'm only going to look for the steady state problem. Steady state meaning u is a function of y and of t, but I'm not going to try to satisfy an initial condition. So what do I have? Well, same ones as before. No. I have symmetry. And no slip. That's the problem I have to solve right now. So here's the dirty trick time, right? Dirty trick time is still using the linearity of this problem, right? So you go, I'm going to look for a function, right? What's the function form I'm going to look for? Say, I'm going to look for, oh, not f, right? So you make the educated guess that this So this is a complex valued function, but the real part being the solution. This is this dirty trick that I did last time. And it usually is good for oscillation type problems where you have two variables you're tracking. It ends working if you have more variables. But if it's just a function of y and t, this going to complex and just, trickerily taking the real part and imaginary part still lets you write down some solutions, which is nice. All right? So this is still a separation of variables, too, I want to point out. Right? If you did start this off by saying, right, I'm going to look, you could do the exact same problem like this. Still the same thing. I could begin with this ansatz or assumption of what the functional form looks like. But this ends up having, there's just some hiccups right here. I mean, right, doing this process, right, looks bad. But you can get this, the differential equation you write out for the g prime of t has this solution if you allow g to be complex and then take the real part of it. So it's a trickery thing, certainly. You still don't have to do this, but you have like, you have to do a lot of like Fourier series and integral representations. But somehow the complex trickery lets us sidestep that. And just somehow taking the real part of a complex variable function lets us write more things down. So you've never seen complex analysis, doesn't quite matter. The idea is there's just trickery that you can do, dirty tricks to do math easier. I just find it amazing that it works out that way. So then really, right, we're sort of saying that right, that my g of t is this, and if I take the real part of it, I will return, right, that I will get back the oscillation I have. Notice, too, that the real of this, the real part of this complex function is exactly equal to our oscillation. And that's also hinting you in that that would end up working. But if you ever knew that, right, the more you're exposed to this idea of looking at the complex things of oscillation type things, it can help you make easier. So then we're on the hunt for now this, right? What is that function? Again, what I've done is I've reduced my problem to a partial differential equation now to a PDE. Now this ends up being this solution, right? Now you just have a new differential equation that governs here. It's a first order equation, so there's only one derivative right in there. No, is it two? It should be two. Why don't I have two? I think there's two. You get the one, here's this, and then you look for a solution, right? So then you look up, okay, and then you can write it down actually. Okay, so this is the F. And it comes from just making the assumption that it has this time-varying complex part. I'm looking for a solution with the real part of it, and then you find that. Just speeding ahead. I'm so slow at this one right now, and I don't know why. Okay, so the whole problem is, like, it's sort of like one and done. I'm just done now, right? I already sort of started off by saying I knew what the time variation part was. It was complex exponential part. So then you have to just rewrite then. Right, this is not Reynolds. I'm saying take the real part now. Right, of this, where this is actually here. So again, you can do Mathematica for that. Right? Mathematica does have a function that I think it's just real of a function that you give it. Right? This coming from an ODE I defined by a separation of variables. So every step along the way, you can just do in a Mathematica book along with me. I encourage you to do that because I want people to be faster at doing math that way instead of pen and paper. Students should be approaching that, not doing it with pen and paper anymore. Okay, so then if you did do that, and this is my ending for this lecture, because again, we do have the solution already. If you did just ask for then this real part, you would get an enormous expression. If I wrote it all out, it would just take me too long. I'll put it on here right here. This is the expression that you would get. And it's in the notes, but I just want you to appreciate how horrible that is. It's absolutely useless to me as a human. I can't interpret every single one of those hyperbolic cosine functions at all. If you turn that into me, I will be very mad. I don't think we should be doing that. So this is a time for you to notice. If you can notice that there are recurring patterns in the solution, right? So while Mathematica would spit out a very large expression, if you look at it enough and then redefine things, you would get this. Okay, so I don't want to write it down because I'm running out of time. This is what Mathematica spits out for you. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 different expressions to keep track of in just one thing. What am I going to do with that, right? It's like, sure, it's right? You can program it. You can plug it into a computer and make plots with it. That's fine. But I don't know what that means. Now, by me redefining things, I can get closer. Okay? So what I've done here is I've just redefined things in that giant expression, and they look like this. And this is the most important thing. This is a constant value based on here. So one thing you'll see that is everything ends up being normalized by this square of hyperbolic cosine functions. Okay? So again, this is just a process of redefining things. Right? Solution's there. Technically, we found it, but I really have been excited for just this part of the lecture. I took 2 problems, just write out solutions, and then they're kind of easy to interpret. There's an infinite series. But now for this one, I did it again, but I'm kind of getting at this point where if you plugged it out, you'd have this expression. But I want you to appreciate that if you just said, oh, I have the same thing dividing these terms, then you would be able to go, I'll define that then like this. Now I can separately go in and see how gamma affects this normalization term, and you can as well. This can be Desmosed. Right? It's nice to see how gamma affects this term. Clearly, if it gets large or small, that means I'm killing off the y variation in my solution. We don't get there yet. And then these m's and n's, I've just, right, I defined them in my notes. Go take a look. But I've just redefined expressions. This one ends up being pretty important because this is going to be able to kill off the functional variation. So I won't write out what the parameters are. Most importantly, there's this expression right here, the j of capital lambda, where it's the square. So it's a positive number. So I'm not going to be able to, right? So importantly, you see that this won't be able to change the sign of this expression. And then also you can get interpretations that really have to track how big this j term is. I can do that, right? I can plot that and see if my gamma is really large, right? I see no y dependence. My gamma is really small, right? This starts getting more and more important, and then other things will occur. Other things I can do is I can then take limits of my redefined things. So a common thing that pops up, right, are these types of expressions. So I have a c, let's say, of x. I'll define that as hyperbolic cosine x. And then let's say capital S. I'll define that like this. So it's just redefining things. If you did Mathematica, it would just spit out every simple expression for you. Okay, now I have these expressions of c and s I can have. So really j, right, even in that definition, I could now redefine this as really just c of lambda squared plus s of lambda squared. But in this form, I can take limits. Okay, so let's screw the whatever, that's the solution. We're about interpreting solution, right? So now by redefining this, you can just either graph it, but you can see, right, as this goes to 0, infinity, which one should I have? What's important for me? Okay, so as this goes down to 0, that c function goes to 1. And then as this goes to 0, this looks like x squared. No interpretation would come from that original expression that we wrote down. Here's where I can say things, right? Because, right, this is just being a function. So now I can see as my gamma value goes down to 0, this term looks like 1. And as gamma goes down to 0, these s terms look like just x squared, getting better. I can look at more effects of things like that. Okay, so all of that to say, if you then redefine a bunch of expressions and look at how you can limit now gamma, now I can get better variations, right? Because now I can look at just what does my solution do for this oscillation when my gamma term becomes pretty small, okay? And then you just get that's a solution for a small gamma. Now, what was gamma? Let's go back to what we defined gamma as before. It was a ratio of length scales, right? It's a ratio of length scales. You could interpret it another way, too. Yes, gamma. Go back to gamma, right? Because now I can interpret what gamma is, right? Okay, that's how I defined it. There was a little square root of the rho over omega. Okay, so what does this mean when this term is going down to 0? Anyone? Anyone? Bueller? Bueller? Okay. Well, it means that, right, if this is going down to zero, right, if this is going down to zero, it means that like the slot length is getting extremely small, or the diffusion length is getting much more important. So for this number being very small, I have this interpretation now that the viscous effects, or the viscous length of it, are much larger than the actual slot length. So viscosity is dominating throughout the entire, right, regime of it. Right? Gamma being large means that the entire flow in the oscillation sees the viscous shearing forces. And you see that here because if this is very small, I really just get the same slot flow I had before, but this quasi-steady, right? Oscillation part in there, where quasi-steady meaning I have a bunch of steady-state solutions as if there were no time variation at all. But quasi-steady means that you can just paste together steady-state solutions, right, with this sort of time component in there. Right? So notice that comes about just from actually limiting this equation down for the lambda going to 0. Another way we can do it. So the other interpretation of this is you can have it be in time scales too, and kind of the exact same situation, right? This could also be thought of as my viscous time scale over, right, the period of oscillation. So the viscous time scale being small compared to the oscillation time is another way to interpret this, right? Or the outright, or right. So this being 0 being that there's just a vast, vast difference between these two things, okay? So how about this being the period? Yeah. Okay, that's the really good one I like. So we have lengths, we also have a time interpretation. Okay, so before this was the h on top, and then this, right, and then this was an h on top, and then this was the square root of nu divided by omega. But now you could actually just have this be h divided by the square root of nu omega, then this period going on top. So this one also says that as well. If lambda is going to 0, that means the period of oscillation is on the scale of like years or months. So more of like a global time, of like a global flow type situation. That makes this 0, and that gets this quasi-steady state based from this analytical solution right here. The second question we have then is this process, well, what if it's really, really large? Okay, if it's very, very large, then I can again take my limits of these expressions here. Now, when it's getting very, very large, what's going to happen is, again, you have to look at what these limits are and how they're defined. So what do I get for large? Okay, so for large, again, these expressions are easier to take limits of if you define them in the way we did previously, right? Okay, that means that these end up looking like exponentials. Right? So these, when these limits are pretty large, it ends up being like the function just behaves like an e to the x with some oscillation in that exponential growth. And you could only take that limit or look at that approximation by redefining the c's and the n's. Look in the notes for how these pop up. I'm just saying I've gone from this trickery of how to get the solution, and I made this argument that if you had Mathematica and just spat it out, it's utterly useless and doesn't help you. But in this form, you can kind of see I really just have to track the size of j. Okay, and j was defined as the square of c and the square plus the square of s. If I take limits, these things will happen. Well, then guess what happens then? Right? So that means as lambda blows up to infinity, this number, right, becomes so large that these don't matter anymore, right? So I get a 0 and a 0. So then that means this, right? So this is for a very fast capital lambda. That's an interesting solution as well that we can get, right, that we have. this means that the oscillation time, the period of oscillation, is so small, right, that I have very fast oscillation happening in this slot right now, that there's no time really for the viscous forces to even, right, there's no time for the viscous forces to even react to what is happening. So this solution now looks like just really a line, right, that's sort of going back and forth via a sine, right? That's really, so the idea that if I have extremely large capital lambda, it really just looks like a line, like an actual pressure pulse going back and forth in the slot. That's also an interesting limiting solution. All of this being able because I just could define and note and write the solution in this form. Because I just had to look at the relative size of this lowercase, of this j capital omega. Look at limits of when lambda was very large or very small. So there's still an issue, and that's going to tune us into really all of next lecture where we do these variables. And that is this problem right here, that when I had an infinite capital lambda, I now violate no slip. Okay, that's not okay, right? When this doesn't even care about y anymore, right? Now I have this issue where now u at the wall is not 0 at all. That means that there has to be some sort of length scale where my velocity has to get down to 0. And how do we connect that length scale? And that's really a large question of most fluids, right? Okay, the solution looks like from afar just this straight line is a pressure pulse by sine of t. But I know for a fact via experiment and just physical theory that at some length scale here, I have to get down to 0 velocity. So there is some little tiny amount of length in there where this had to occur. So one way to think of this then is if I have just these coordinates here, I really can still think about it this way. Okay, I know that h has to be the summation, right, of my y coordinate plus some other coordinate I'm going to call eta, right, a scale, some sort of length scale. All this is saying is this is always h, and there's some there's some scale y which looks like this sine of t part here, but as I get closer and closer and closer to the wall itself, there has to be some other length scale, right, that looks like this. So then solving really just for what that eta is, right, it's that. And now I can do a non-dimensionalization on eta, right, so non-dimensional eta. What do I get then? So now for the non-dimensional eta, or an eta star, what do I normalize by? Well, I'm normalized by my viscous length scale. Okay. So the number one issue you would have is not scaling by this length. What did I not scale by? I didn't say that I did not say that this length scale or this amount of distance away from the wall. What I did not scale it by was by h, which is what I did in the previous situation. Before, I said all of y scales like h because it was the domain of my problem. This is a slightly different issue, though, because in this limit right here, I can't retain that idea of no slip. And no slip is a fundamentally viscous property, right? No slip arises from the fact that while you could have velocity in the free field, at some length scale, it has to get down to being 0 velocity at the friggin' wall. So the normalization should certainly be the viscous length, not the h, because I can't capture that here. So I now non-dimensionalize this way. And this now gives me this eta star. Okay? And again, all of this coming from the fact that you're just going, you're breaking your coordinates up into now two different coordinates, where this one y really looks like the h in the slot, and this one eta is all about this, is measuring only this viscous part of the flow, where the shearing forces get the velocity down to 0 right by the wall. Right? And all that happens here then is you now have to then change your, you now have to change all the coordinates and differentiations in here, right? So you switch these things up, essentially go from now a y star to an eta star in this expression, and then take your limits, you'll recover a different solution. So if you do this eta process, I can retain a length scale in my limiting of this. And you just get really an extra part. That's it. So we had an issue arise when we had this very large, right, when we had this very, very fast oscillation. The oscillation was so fast that the flow itself behaved in a limiting sense of getting the actual solution to being just this line that varies like sine of t. But if you look at sine of t, I can't obey no slip. What I have to obey a no slip. That's physical law. It's almost like Newton's second law in fluids. So I now come up with this idea that h is the summation of two variables now. One of being y, and now one being this eta term. Non-dimensionalize that with a different scale, and now I have a situation, now I have this. Right? And that allows you then to write these y etas in terms, the y stars in terms of the eta stars, then you retake the limit in infinity, and you get this extra term right here. And I want you to see how this actually does become 0 at the wall now. Right? Isn't that interesting how it seems so clear that like when eta star is equal to 0, well, I get 0 at the wall. Now everything works pretty well. And then when eta goes off to infinity, so if I'm at the wall, right, the interior of my slot looks infinitely far away. What happens there? Well, infinitely far away in terms of viscous length scales, this goes away, and I just have the sine of t recover the same dynamics. So I think that's interesting that you learn a lot from these solutions. But there's one other thing sort of that we haven't done, and that's the situation where if I have all of my solutions that I've done in this limiting process, right, sort of take a stance, right, take a gander of what we've done. What we've really done so far all day is we've had solutions that lie on some sort of line, especially in this one. So this is like capital gamma scale. So today what we did is we did a very rigorous sort of analysis, right? And we've gotten sort of a handle on what solutions look like, what the U star looks like, what the velocity profile looks like in the cases when this goes to 0 and the cases of this going to infinity. So we have taken care, at least in this case, and think about the other cases too with this phi going forward and backward, right? But that actually had no slip all the time. So in this situation, what we end up having is I now have right? I have solved for all slow. I have a handle of how the solution looks like if it's a very slow oscillation, and I have a handle of what it looks like for very fast oscillations. All right, and the methods of really like filling in the blanks right here, right? Having uniformly valid solutions over the entire domain of parameters is next lecture. And that's my favorite part of math, that if I were to rank it. I think this process of having uniformly valid solutions is 100% my favorite part of applied mathematics. OK, I got a little more energy. Next time we're doing 3 other problems that are rotational, and we're going to go more on this scale thing right now. I think my notes are certainly better than my lecture today. But I'm going to get a coffee, and then I'll have more energy next time. Also, one of my favorite artists has released a new album today, Cloud Kicker, and it's like so good. Anyway, I'm way over time, but let's do harder problems next time.